Who are watching on the camera will be a little bit dizzy right now. So, what if we wanted to go to R4? How would you denote variables in R4? What would you do? Yes? I'm sorry? Well, you have to add some letter, so you said you would add an alpha?
Yeah.
Okay, why alpha?
Because I don't really remember, but I think that after Z you would start adding Greek letters.
One possibility is to do a Greek letter. Some people like to use W. Do you put a W before the X, because it comes alphabetically before the X? Do you put the W after the Z? There's a great Dr. Seuss book, On Beyond Z, where he creates new letters of the alphabet. Well, eventually you start running out of alphabet letters. There's only finitely many alphabets in the world. Even if you use all of them, you will run out of letters. That's the power of notation like this. X1, X2, Xn. It's very clear. X4 always means the fourth component. If I put a W before the X could sometimes be the first component, sometimes it could be the second component. This is really good, powerful notation. And that's what I want to emphasize today. That's why we use something like this. Okay? We could use Greek letters, we could use W's, but we will eventually have trouble. It allows me a very clear, concise way of writing everything down. Okay, so now we have a notion of what it means to have a function from an input set to an output set. And we have an idea of what we want our input sets to be. Our input sets could be things such as your location on the center on the Earth, your latitude and longitude. Or if you're not so parochial, your location in the Milky Way measured from the galactic center. You'll have your radius and then your latitude and longitude. Okay? So now this brings us to the notion of vectors. So a vector has length or magnitude and direction. So a vector is generalizing a notion from one dimension. In one dimension we just have a number. We have a little bit of a notion of sign in one dimension. Positive numbers going up, negative numbers going down. A vector allows us a little bit more freedom. So for instance, if I take V to be the vector 3, 4, what I mean is I go over 3 units, I go up 4 units. And this is my vector V. So again, for the most part, I don't like New York City. What is the one thing where I will tip my hat to New York and say you do better than Boston? Yes? The grid. The grid. Manhattan is a beautiful grid. It's very easy to talk about north, south, east, west. We can't do that nearly as well in Boston. I know, and I will be seeing that again tonight as I try to get to my hotel. Okay? Here, I can express V as so many steps in the east-west direction, so many steps in the north-south direction. And so what we're going to do is we're going to introduce notation for some really good vectors like this. So if I give you vector V3, I'm going to let E1 be the vector 1, 0, 0, 0 in Rn. I'll let E2 be the vector 0, 1, 0 in Rn. All the way down to En is 0, 0, 1 in Rn. So these are unit vectors in the coordinate directions. So unit vectors in the coordinate directions. And the idea is we can express any vector nicely in terms of these directions. So when I give you the vector V equals 3, 4, I can write it as 3 times the vector 1, 0 plus 4 times the vector 0, 1. So I'm not going to go through the proofs of all the vector properties. I want you to read them. If you have questions, let me know. Essentially, everything you want to hold for vectors holds. If you have 2 vectors, you add them component-wise. Okay? It's generalizing the notion of adding numbers. Multiplying vectors is more complicated. We'll talk about that later. Well, what's the vector 1, 0? I could write this as... Okay, so you read ahead, good. How else could I write 1, 0 in terms of what's on the board? As E1. So I could write this as 3E1 plus 4E2. So we'll talk about the IJKs in a little bit. I don't like the IJKs, but I know we have to have them. Okay? The whole point of vectors like this is to make it easy to talk about more complicated vectors. These are my building block vectors, my coordinate directions. And you give me any vector, I can represent it as some amount of E1, some amount of E2, some amount of E3 if I have 3 dimensions, and so on and so on and so on. Notice I'm writing my vectors with an arrow over it. Some people prefer to write vectors by writing the vectors in bold. Well, on a blackboard that doesn't really work as well. And then you'd have me shading things in, and now, this is, takes a lot of time to do that. Sometimes people use capital letters. If you think back to Calc 1, Calc 2, use big letters for antiderivatives, integrals, little letters, lowercase letters for the derivatives. The whole point of this is to be able to quickly look down at the paper and get a sense of what's going on. I want notation that speaks to me. I want notation that I can look at and say, ah, yes, that's what I'm talking about. If I put an arrow on it, okay, numbers don't have arrows. So I can quickly look down at V and say, okay, something must be going on. This is the vector V. It's not a number. Okay? And so the next question is, if I give you a vector like this, a vector has magnitude and direction. So when I write it as 3, 4, I've encoded everything together. You can view it as I'm starting at the point 0, 0, I'm going to the point 3, 4. This tells you how I'm going. What vector do you think goes in the opposite direction? So W, say negative 3, 4, or negative 3, negative 4, is in the opposite direction. Okay? So now I can do anything you would expect to vectors with vectors. If I give you 3, 4, and I add 8, 2, this would be 3 plus 4, I'm sorry, 3 plus 8, and then 4 plus 2, so it would be the vector 11, 6. And if I gave you 2 times the vector 3, 4, that would be 2 times 3, 2 times 4, or the vector 6, 8. I'm not going to go through the distributive and the other properties, but you combine vectors the way you would expect. If I add vectors, I'm adding them component-wise. If I multiply a vector by a number, I just multiply every component by that. The way you should think of this is 2, 3, 4 means the vector that's in the same direction, but is twice as long. I'm dilating it, I'm expanding it by a factor of 2. So it would be a vector like that now, and that would be bringing me to 6, 8. Any questions on what we've done so far? So we've defined the natural numbers, the real numbers. We've defined what it means to say R3, R4, R5. R3 is triples of real numbers. R4 is quadruples of real numbers. Rn is an n-tuple of real numbers. Vectors have magnitude and directions. These are really good vectors to use. Yes?
What's that symbol before the R?
Oh, this means element of. So it just means this is an element of Rn. It's a n-tuple of real numbers. Yes?
I just have a question on
Yes?
vector notation.
Yes?
So in the book, they sometimes see the arrow instead of the bracket.
Yes, I'm about to get to that. And so what I want to do now is just talk about alternate notations. And so there's that, and there's the IJK. And so, unfortunately, different people use different notations. So what I want you to know is just other notations. So sometimes people use AB with an arrow for the vector from A to B. Another notation people use is instead of writing V equals 3, 4, they do angular brackets 3, 4. And what a lot of people, including our book, will do is they'll use the angular brackets like this to represent a vector, and they'll use the parentheses to represent a point. Well, if you think about it, if I give you a point, that's really the same almost as giving you a vector. And so I'm a little bit more, fast and loose in terms of what I will use to denote a vector and a point, because they're really equivalent. I can evaluate my function at a point, I can evaluate my function at a vector. Whenever I do something like this, it's always coming from the origin. I just prefer writing parentheses than writing angular brackets. I think it's a little cleaner. There's always the danger of something like this being mixed up for a what? Sloppy handwriting happens. Greater than or less than sign. So I find this notation very dangerous. So again, I strongly urge you to write cleanly and neatly. Okay, and that's really the main reason I prefer this. You don't have commas in the middle of a mathematics equation. How many of you have read James Joyce? Is your hand up?
Yeah, no,
Okay, so a lot of times people say, you're too young to truly appreciate Joyce. And maybe when you're older, you can appreciate how many pages without a period?
There can be a lot.
I mean, it's easily in the tens of pages without a period. Just very long sentences. And when you're older, you might appreciate it. I'm being recorded, so I have to be polite. Okay? In math, you do not pause for dramatic effect in the middle of an equation. And we find x equals... You're not going to have a pause like that. You're not going to put an exclamation point in a math equation because you're excited. An exclamation point in math means? Factorial. 2 exclamation points back to back means?
Factorial twice.
No, it actually means the double factorial, which is not the factorial twice. Factorial doesn't really occur that often in mathematics. The double factorial means you take every other. So 5 double factorial is 5 times 3 times 1. That occurs very often. I have had math papers where I've had double factorials followed by an exclamation point for emphasis. But you really have to avoid stuff like that. Right? We don't have pauses. If we have a parenthesis like this, it's clear that we have a vector. The other notation that people like to use is I is the square root of -1, but if we put a hat over it, which is good this time of year, this means a unit vector in the x-axis direction. So this means the vector 1, 0, or if we're in 3 space, 1, 0, 0. J hat would be the vector 0, 1, or 0, 1, 0. What about k hat? What would that be? It would be, yes?
Only in the
Excellent.
3-dimensional scale?
Why only in?
Because there's no other variable to manipulate beyond I and j in the 2-dimensional.
Okay, say that again?
Well, there's only 2 things to work with in the 2-dimensional scale, and if you're adding a third thing, then what do you do? So it must just be...
Good. So if I have 3 components, I'm not talking about something that lives in a plane, because I have 3 components. If I just talk about I hat or j hat, I could be in the plane or I could be in 3 space. It's not clear. If I have a k hat, I have to be in 3 space. So whenever you see I hat and j hat, you have to look from context, where do we live? Okay? I really don't like the I hat, j hat, k hat notation. But you should be aware that it exists. Okay? Any other questions about this notation here? Okay, so we've got the notion of what it means for it to be a vector. We have components. We have all the different things we can do to the components. We want to figure out what is the length of a vector. I mean, one of the things I keep emphasizing is vector has length and magnitude. Well, let's go back to a vector 3, 4. This is an extremely well thought out lecture. This is one of the advantages of being at the 11 o'clock class rather than the 10 o'clock class. Why do you think I chose the vector 3, 4? So we're talking about lengths now. Why do you think I like the vector 3, 4?
Because it forms a 3, 4, 5 right triangle.
It forms a 3, 4, 5 right triangle. So here's 3, here's 4, here's 5. And so if I give you the vector 3, 4, we know its length. So the idea is we can get lengths of vectors through Pythagoras. What I want to do now is I want to motivate why the next definition works. I do not want to give a full-fledged proof of how you calculate the length of a vector in, say, 2014 dimensional space. I will talk about how you calculate lengths in a couple of dimensions, and then give you an idea of why it's true in general. And if you want to know more, I'm happy to chat with you. I'm happy to write something up. I don't want to overload you with proofs, but I want you to get a sense of what's going on. So let's let V be the vector V1, V2, Vn. Denote its length by absolute value of V or double lines of V. So I like both notations, but in some sense I do prefer one notation to the other. Which notation, and I know you've only known me for like a class and a half now, which notation do you think I prefer and why? Yes?
The 2 lines because it differentiates from absolute value.
Excellent. It differentiates. It's something new. When you see the double lines about V, it's like, oh, I'm doing a length of a vector. It's reminding you, I have a vector that's being studied. So again, I like visual clues. As an aside, if I give you the integral from 2 to 3 of x squared dx, what's going from 2 to 3? I heard it from back here. What's going from 2 to 3? Yes?
Your x values?
My x value. X goes from 2 to 3. This is what this notation means. X goes from 2 to 3, and I'm finding the area under this curve. Do I need to be extremely redundant and write x goes from 2 to 3? No, there's only one variable under consideration here. The only variable that's under play is x. This is absurd. But I will love to do this in Calc 3. Why do I like doing this in Calc 3?
Because multiple variables.
There's multiple variables. So we will eventually all swear to uphold the convention of which order you integrate. And if you write dx dy, that means one thing. If you write dy dx, that means another thing. And we will all promise to honor that. But why not make life easier? It's so easy to just write x equals down below so that you can quickly look down and see what's moving. Is it necessary? Absolutely not. Math is hard enough as is, right? Why not take a little bit of time and make things helpful? There was a famous mathematician who was proud of the fact that his book had not one picture in it. Okay. He was a beautiful mathematician, but his expositions left a lot to be desired. Take the time. Make your work easy to follow. How many of you have ever written code in computer science, in programming? How many of you do a good job commenting? I can't keep my hand up. If I need to read my code, it's not a problem. If someone else needs to read my code, it's often very difficult. It's good to get into good habits. Okay? So again, I will use either notation. In some sense, we're overloading the notion of an absolute value. Well, let's think about it. What does the absolute value of 5 mean? Yes?
It's the distance from the 0 point to...
Good, it's the distance from the 0 point. So, absolute value of 5, or absolute value of minus 5. So the absolute value of 5 would be this distance. And the absolute value, here's 0, here's 5. The absolute value of minus 5 would be this distance. So in some sense, the absolute value is measuring the length of a vector. It's measuring lengths of these one-dimensional vectors. And if you want the absolute value of x, here is a formula for the absolute value of x. Okay? If you want to laugh, by all means laugh. I won't be insulted. The absolute value of x is the square root of x squared. Okay? I've taken a very nice thing like absolute value and I've now expressed it as the square root of a square. But this now works for both positive and negative numbers. It's beautiful. And this is something that I can generalize. And so the length of v is going to be the square root of v1 squared plus v2 squared plus vn squared. And what you can see is this is really going to do a great job of generalizing our notion of absolute value. This is why I wanted to write the absolute value of x first. This is a great definition. Now the only problem is, does it have the properties we want? Does it actually give us the length of the vector? Well, we can find lengths of vectors by Pythagoras. So all I have to be able to do is draw a triangle. And the way we're going to do things is we'll just keep drawing triangle after triangle after triangle. The easiest case to check this formula is when n equals... No, a little bit easier than that. Yes? One dimension. Right? The easiest case to check Pythagoras, to check the notion of length is one dimension. That's our notion of the absolute value. So, check when n equals 1. It's just the absolute value. What's the second easiest place to check? 2 dimensions. Check n equals 2. It's true because of what? I think I heard somebody say it. It's true because this?
Pythagorean.
Pythagoras. Right? In 2 dimensions, here's v1, here's v2. This is the square root of v1 squared plus v2 squared. That's its length. So in 2 dimensions, this is just the Pythagorean formula. Okay? So now the question is, why is this true in higher dimensions? So what I want to do is I want to just do a sketch of the proof in 3 dimensions. It uses a concept called mathematical induction. How many of you have heard of induction? Induction basically means you take your statement and you reduce it to a lower dimension, a simpler statement that you know to be true, and you kind of build up like a staircase. So again, I'm not going to go into all the details right now of how do you prove things with mathematical induction. If you want to, happy to chat about it. But I just want to give you a sense of why it's true. This is the real challenge in this course, is to balance how much proofs to give you so you can believe what I'm saying versus how much proofs you want to see. Okay? I'm hoping that's a positive number. So, let's do 3 dimensions. Now, of course, my 3 dimensions is not so great to draw on, but imagine I have a vector like this coming out. I can draw a vector in the xy plane below it, and then the z part is coming straight up. So if you want, here, so here's my xy plane, here's my z-axis, coming up like this. And maybe here's my x-axis, and here's my y-axis, and here's my vector. So I can form a triangle like this, okay? And so here, it's going to be v3, e3, right? And now over here, I'm going to call this vector down below as v12, and I'll worry about what v12 is later. Okay? It's just something in the xy plane. I can figure out what that is later. The length of my vector v, by Pythagoras, it's the square root of v3 squared plus the length of v12 squared. That's just Pythagoras. Okay, so now I'm reduced to figuring out what the length of v12 is. Well, how do I figure out what the length of v12 is? What do I use?
More Pythagoras.
More Pythagoras, right? What could be better than Pythagoras? 2 Pythagoras. Pythagorean, much better. So here is v12, and then I would have it as v1 and v2. So the length of v12 would be the square root of v1 squared plus v2 squared. And I just plug that in here. And that would be the proof. Okay? So this is where we would get our notion of length in 3 dimensions. Okay? So there's a lot going on here, so let's just quickly review. We have the absolute value, which is giving us the notion of length. It generalizes to vectors, and the way we're going to define the length of a vector is the square root of the sum of the squares of the components. When you think about length, what kind of quantity should length be? Be very careful. It's very easy to get this slightly wrong. What should length be? What kind of number? Almost. Yes?
Natural?
Not necessarily natural. It's a little bit more than just positive. Something else is allowable. Who knows about the Houston Astros from last year? What were the Houston Astros famous for last year?
Being bad.
Being bad. Okay? They won less than 1 out of every 3 games. Okay? If you look at the Houston Astros win streaks, no matter how bad the Astros are, their win streaks were never -2 games. What's the smallest win streak the Houston Astros could have? 0. That's a perfectly acceptable, okay, maybe as an Astro fan it's not acceptable, that's a perfectly realizable number. They can have a win streak of 0. You can't have negative values. So for length, I have to be able to allow 0. And if you think about what's going on, v1 squared, v2, even if these numbers are negative, their squares are non-negative. And so the sum of the squares is non-negative, their square root is going to be non-negative. So I will get that the length of my vectors are greater than or equal to 0. Okay? Yes?
Sorry, could you just quickly run through your steps again once you went to 3 dimensions?
Sure. So when I have my vector here, I have some part of the xy plane underneath it, and then I have v3, e3 going up. And so I first form this triangle. And in this triangle, the side coming up is v3, e3, and I have some vector v1, 2, say. And by Pythagoras, the length of the vector I care about is v3 squared plus the length of this vector squared. And now how do I figure out the length of this vector squared? I use Pythagoras again. This lives in the xy plane. So I now decompose it as v1, e1 plus v2, e2. And its length is going to be the square root of v1 squared plus v2 squared. I just plug this in here, and then when I square it, the square root cancels, and I get v1 squared plus v2 squared plus v3 squared. So again, I hope it seems reasonable that something like this will work in higher dimensions as well. That this is going to be true not just in 3 dimensions, but in 2014 dimensions. And we now have a really good notion of length. And that this length will be non-negative, it will have all the properties you want.
So basically, in that, like, for each dimension, you just keep putting in another triangle underneath.
Yes. Now the important thing that what we're doing here as an aside is that our directions are perpendicular. Okay? If we use the Boston directions, that would not necessarily be the case. And so, how many of you can speak another language? How many of you can speak another language well? Linear algebra, which is a great sequel to this class, is really like speaking another language. If I had to guess, so this is an aside, which part of Algebra 2 did you hate the most? I would go with conic sections. And writing down equations of ellipses and hyperbolas and all that. If I had to guess, that is where I would put my money. You might remember, if I give you an ellipse like this, it's of the form x over a squared plus y over b squared equals 1. That's a, negative b, b. You might remember that. Almost surely you will not remember how to write down the equation of this ellipse. It's not that much harder to write down the equation of this ellipse. What you do is you basically lean back like this. Okay, if I'm leaning like this, what does it look like now? Yeah, it looks like a normal ellipse. I change my coordinate system, and I express it in this new coordinate system, and then I lean back again, and I convert backwards. Linear algebra is all about translating from one coordinate system to another. For the most part in this course, we are only going to use the Manhattan coordinate system, the grid coordinate system. There's a couple of exceptions. We will use polar coordinates, cylindrical coordinates, and spherical coordinates. So, what do you think spherical coordinates will be good for? Spheres. I can't really hide where to use spherical coordinates. What do you think cylindrical coordinates will be good for? It's going to be a great semester. We haven't even covered the coordinate systems and you already know what's happening. Polar coordinates is a bit tricky. We don't call it circular coordinate systems. You have to remember to use polar for circles. Right? Those are the 3 main coordinate systems we will use other than the Manhattan grid. When I'm trying to represent vector lengths, it's very easy when I do things like that. I could do a Boston coordinate system where these are my 2 directions. And if I give you this vector here, or I would now write it as something like this plus something like this. And now it's not so clear what the length would be in terms of stuff like this. This is what you'll get into in linear algebra. And there are times when you want to use other coordinate systems. If you are given an ellipse like this, that's a great time. Right? For the most part of this class, we're going to use the standard coordinate systems. Okay. Any other questions on the material we've done before we do a few more examples and then the last idea of the day? Okay. Whenever I do an aside, I will try to write aside just so you know that this is advanced material. I just want you to get a sense of what's coming so that if you decide you want to continue in math, you have a sense of what will you see. Is this something you want to see? Okay. Let's do unit vectors. So if I give you u is 3, 4, then the length of u is going to be the square root of 3 squared plus 4 squared. This is the square root of 25. This is just 5. So, unit vector in the direction of u, we will write that as, how do you think I'll denote a unit vector? Instead of using an arrow, we use a hat. Okay? Just like we're doing with the I hat, J hat, K hats. I put a hat to mean it's a unit vector. this is going to be the vector u divided by the length of u. And that will be 3/5, 4/5. So it's frequently useful to have a unit vector in a given direction. Right now, the way you should look at what we're doing is we're building a strategic reserve. We're putting material in the bank so that when we get to calculus, we will have the language to describe functions of several variables. This is all building up the language so we can talk about the advanced mathematics. Okay? So I do apologize. It's not always exciting to be learning all the different linguistic terms, but we need this to have the conversations. Another example that I want to do is imagine I give you two vectors. Here's the vector p, and I'll call it p1, p2, p3. Here's the vector q, I'll call it q1, q2, q3. I could call it x, y, z, or maybe x1, x1, y1, z1, x2, y2, z2. Lots of different choices for notation. I like to use p and q because I can quickly tell, oh, okay, p probably coming from the point p, q probably coming from the point q. If I want to calculate this vector here, well, I have the vector p plus something equals the vector q. What vector do you think this is? So p plus what should equal q? What should go in there? Yes?
Q minus P.
Q minus p. So remember, when we add vectors, we add component-wise. Things are commutative. In general, in life, things are not commutative. If you add numbers and take the square root, that's different than taking the square roots and then adding. Order typically matters. Okay? Here, I can subtract and add in any order. The p's cancel, and that will just give me the vector q. And so if I think about what's going on, this vector is going to be q1 minus p1, q2 minus p2, q3 minus p3. And this is the vector q minus p. The vector p minus q is going in the opposite direction. Q plus p minus q would be p. And this allows me to just express vectors very nicely in terms of the coordinates of the starting point and the ending point. And we will do a lot of this in calculus when we're looking at here's where we start and where are we a short amount of time later. Okay. Any questions on what we've done so far? Everything good so far? So we have about 4 minutes left for the last concept of the day. We're just going to make it. Okay? Okay. We've talked about length. We've talked about adding vectors. There's another operation that we should generalize from normal numbers. What else can we do with numbers? We can add them, we can multiply. So, for the most part, I'm not going to do too much from section 11.2 because we just did it. A lot of 11.2 is just doing 11.1 again with several components. But there is a major difference between 2 dimensions and 1 dimension. How do we do multiplication? So dot product generalizes multiplication. And so if I have P is P1 through Pn, and Q is Q1 through Qn, I'm going to define P dot Q to be P1 Q1 plus P2 Q2 plus dot 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 plus Pn Qn. Again, I can do anything I want, I can define anything I want. Sometimes they're good things to do, sometimes they're bad things to do. Does this look like a generalization of multiplication? Well, if we were doing Calc 1, how many variables would we have? So how many variables in Calc 1? 1. Alright, so basically if we had one variable, we would get P dot Q is P1 Q1. Does that look like multiplication? Yeah. This seems like a nice way to generalize multiplication. If I had just one component, I would just multiply it. Why is this the right thing to do? Why don't I take sums of square roots? Or why don't I have maybe a factor of 1 here and a 1/2 here and a 1 over n here. It's not clear at all why this is a good thing to define. Right? I will explain the following theorem, why it's true, on Wednesday's class. I'm going to just state it now. So imagine this is P, imagine this is Q, and let this angle be the angle between P and Q. Then we have the following beautiful result. The cosine of this angle is P dotted with Q over the length of P times the length of Q. And again, in the interest of full disclosure, within a couple of years, most of you will reach the point in your life where you will never, ever, ever do this again. Okay? You haven't reached that point yet, okay? You'll be doing this for, a lot over the next few weeks. But I want you to look at this formula, and I want you to get a sense of how to look at formulas and see, are they reasonable? If I double P, what does that do to the angle between these two vectors? Does it change it or not change it? It doesn't change it. Let's think what happens. If I double P in P dot Q, okay, I want to double the numerator. The length of P is the square root of P1 squared plus P2 squared plus Pn squared. If I double P, each of these components increases by 2. When I square them, they increase by square root of 4 is 2. So the denominator increases by a factor of 2, the numerator increases by a factor of 2, there's no change in the ratio. If I quintuple Q, okay, it's a fun word to say, quintuple, right? The numerator increases by a factor of the denominator. No change. So this is at least a reasonable formula. It has a chance of being correct. Okay? What would be the easiest angle to understand? If I had to give you an angle, what angle would you like? You sorry? 0 or 90. And so we'll end with, if you take P to be 1, 0, and Q to be 0, 1, P dot Q is 0. And this leads to an angle of 90 degrees. And when is the cosine 0? At 90 degrees. Alright, so again, a lot of stuff that we did today. I apologize for the blitzkrieg of notation. It will continue a little bit through Wednesday, but hopefully by the end of this week we'll have covered most of the notation we need to do. And then within a week or so we will actually start doing calculus, as the name suggests. Okay.